Hi, welcome to our webinar, Minimizing the Effects of Wind on Air Tightness Measurements. My name is Bill Graber. I'm the marketing guy with the Energy Conservatory, and I've been with TEC for about a year. Today, we're going to hear from Gary Nelson, who's the founder of the Energy Conservatory, and he's going to take us through best practices for minimizing the impact of wind on blower door tests. Now, Gary is still active with TEC. He acts as a physicist, an engineer, and researcher for us. And today's course will count for one CEU with BPI. And if you have any questions during the session, be sure to enter them into the Q&A at the bottom of the Zoom. Just a quick reminder of who we are, the Energy Conservatory. Our mission is to improve built environments, and we help do that for the industry by building robust air measurement tools and processes. That's really been the mission since Gary started the company nearly 40 years ago. And the products we sell, many of you will be familiar with: the Minneapolis blower door, Minneapolis duct blaster, the DG700 and DG1000, the True Flow grid, and associated software. We're a 100% USA owned company, and we assemble our products in Minneapolis, Minnesota. So I'm going to give a very quick introduction of Gary. Most of you that are familiar with our equipment probably at least have met Gary at a trade show or something. And when Gary started the company, his goal was to make blower doors, which up to that point were primarily research tools, and make them pragmatic and practical so that they could be used to test buildings as they were being built. And so sometimes we get asked, did Gary Nelson invent the blower door? And, this is an analogy that Steve Rogers, our president, has used a few times. He wasn't the inventor, but he's sort of the Henry Ford of the industry. And so many of you are familiar with Henry Ford and what he did to make cars available to the everyday man and make them more cost effective. And but he didn't invent it. In fact, Carl Benz was selling practical automobiles more than 10 years earlier, but it was Ford who made them available to everyone. And so that's Gary's role in the industry. And with that, I'm going to hand it over to Gary and let him take us through today's topic.
Thanks very much for the introduction, Bill, and welcome everybody to the webinar on minimizing the effects of wind during blower door tests. You should be looking at an agenda right now along with me, and we're going to split this into two basic parts. One is some background information about what is it that goes on during a blower door test and why is wind a problem. And we're going to get into the weeds a little and go into some technical information about wind effects on buildings from the ASHRAE fundamentals. And then we'll look at some of our data that we've been collecting on the effect of wind. And then we're going to go to the other main section that's about best practices, about this is more about the actual where on exactly the side of the house that we think is best, where is it best to put the outdoor pressure tube, and some other results that are related to the practical aspects of minimizing effects of wind. So we're going to start with just going to talk about what are we doing when we're doing a blower door test. First of all, we usually at least report the results of a blower door test at 50 pascals, or maybe we only do a 1-point test at 50 pascals. But keep in mind that what we're talking about when we say we're testing the house at 50 pascals, it's the induced pressure due to the blower door running that's going to be 50 pascals. The 50 pascals is how much did we change the pressure from whatever it was before we started the blower door test. And so during the test, we turn the fan on and we adjust the speed of the fan until we have changed the pressure difference between inside and outside the building by 50 pascals, or in the case of a multi-point test, we might be doing several different pressures instead of 50 pascals. And then when we get to we call it the target pressure, the pressure that we're trying to change the pressure by, when we get to the target pressure, we then measure the flow, and that's the CFM at that induced pressure. So since we're measuring the change in pressure, and no matter where we are, we'll get the same change, we first have to measure the pressure difference that was there before we turned the blower door on. So we cap off the blower door, and then we measure the pressure difference between inside and outside at some location that we've chosen. And this pressure, probably everybody knows, this is called the baseline pressure. In European standards, it's often called the zero flow pressure because it's the pressure that exists when there is zero flow through the blower door. So if the wind were perfectly steady, so that the pressures between inside and outside the house were steady, they're not changing in time, in that case, it wouldn't matter where we measure the pressure because we have this steady pressure and it's going to change exactly the same everywhere, and it won't matter where we measure the pressure. But the problem is, even when there's a relatively steady wind, there are always fluctuations in the pressure because the wind blows over objects that are upstream of your house, like a mountain that's 10 miles away, or a house that's 50 feet away, or a big tree. And those fluctuating pressures are what can mess up our blower door readings, our house pressure readings during a blower door test. So the problem here is we want to know how much did we change the pressure. So we start out, we measure the baseline, and then maybe 30 seconds later, we turn the blower door on and we get the house up to speed, and we say that we've measured the change from the baseline. But if the wind has changed, either direction or speed, the amount that we've changed the pressure in the house by is how much have we changed the pressure in the house compared to what it was a half a minute ago. What really matters is how much did we change the pressure in the house by from where it would have been if we hadn't been running the blower door test. But we don't know what that is because we can't measure it because the blower door is running and that house pressure is changed. So as we said, the difference, the amount that the baseline changes between when we measured it and when we actually take our flow data shows is really an error in the induced pressure in the house. So I'm going to go through an example here. So imagine that there is an error of 2 pascals in the induced house pressure. That means that when we think that we're depressurizing the house by 50, we're actually only depressurizing it by 48 or 52, depending on which direction that error is in. If we're off by 2 pascals out of 50, that's the error in the induced house pressure is 4%. That actually causes an error in the CFM 50 that we're reading of about 3%. And we'll come back to that. So if the target pressure, though, instead of being 50 pascals was only 20 pascals, and we still had that same error due to the wind and the change of the baseline pressure of 2 pascals, this is now a 10% error, 2 pascals out of 20 pascals. It's a 10% error in the induced house pressure, but it turns out to be about a 7% error in the flow that we measured at 20 pascals of house pressure. So to conclude from what we've learned so far, ideally what we want to find is a location where we're going to measure the baseline and the induced house pressure, where the baseline reading is as steady as possible. Doesn't matter what it is. What matters is how much is it fluctuating. And this is the biggest thing we can do to improve the errors due to the wind. So now we're going to get into the weeds a little bit and go to a couple of diagrams that are in the ASHRAE Handbook of Fundamentals. Strongly recommend this chapter in the ASHRAE Handbook. So what's the best location? What does ASHRAE tell us about the best location? Well, the theory, and we're going to go through why this is the case. The theory says that the ground level on the leeward side of the building is the best place to measure. So here's the first of a couple of diagrams that I'm going to show out of the ASHRAE Handbook. Here we see a diagram showing the wind blowing up against the side of a house. And over here we can see they're assuming that upstream of this building there are no big objects, so the wind is coming along unobstructed. And in this diagram here on the very left, the length of each of these arrows is proportional to the wind speed. And this diagram is meant to show that as you get closer to the ground, the wind speed goes down. And in fact, right at, a millionth of an inch above the ground, the wind speed theoretically should be exactly 0. So we're now going to go look at something about that's related to the pressures that are caused by the wind blowing on a building. And at the bottom here we see just a cross-section plan view of the building. So the wind is coming from the left and it's blowing on this side of the building. So we're gonna look at two cases, and we're gonna look for during this presentation just at two of these. One is where the angle is 0, which means the wind is hitting here, and that's the windward side of the building. And the other one we're going to look at is when the wind angle is 180 degrees, which really means that the wind is blowing over onto this side of the building, and this side that's labeled AD is now the leeward side of the building. I guess I have a detail on the next slide. Yeah, so here's those pictures blown up a little bit. These are the pressure coefficients, wind pressure coefficients on the windward side of the building. And what it means if there's a wind pressure coefficient of 0.5, that means that the barometric pressure or the static pressure on the outside of the building, this is the absolute pressure. We're not talking about pressure differences between inside and outside yet. And you can see that it goes up the least, which is what we're looking for. We want to know, okay, if we don't have any wind and then a gust of wind comes up, where do the pressures change the most? Where do they change the least? Because those are causing the errors due to a gust of wind that comes up in the middle of our test. So the bottom of the house, even on the windward side, the bottom of the house is where the pressure changes the least. On the leeward side of the house, you see things look a lot different. Here on the windward side, you see the amount that the pressure changes depends on where you are on the windward side of the house. On the leeward side of the house, the pressure changes by the same everywhere. And you see that the pressure on the leeward side of the house outside goes down. Another interesting thing that's mentioned in the ASHRAE handbook is that if all of the walls of the house or building are equally leaky, in theory, the pressure inside the house will go down. It also has a wind pressure coefficient. And for a house that's equally leaky in all of the walls, the interior pressure coefficient is minus 0.2. So we can see that the pressure inside the house is doing almost the same as the pressure outside on the leeward side of the house. And that's the whole point here that we're getting at, is the pressure difference between the inside and the outside changes a lot less when the wind blows on the leeward side of the house. This isn't always true, but typically this is the kind of thing that we see is going on when the wind blows. So we're going to go back to the case where, assume that we have a 10-mile-an-hour wind blowing upstream of the building at the height of the roof of the building. And so the wind speed there is 10 miles an hour, which means that the velocity pressure of the wind at that location is about 12 pascals. And then on the windward side of the house, the outside pressure at the bottom over here, the pressure on the outside, on the windward side at the bottom, is going to increase by 6 pascals. The internal pressure is going to go down by this 0.2, which is the wind pressure coefficient for the inside of the house, times 12. We multiply by the same wind pressure, or the velocity pressure of the wind. So the house pressure is going to go down by 2.4. And since we're measuring the pressure difference between the inside and the outside, it's going to change by almost 8.5 pascals. On the leeward side of the house, however, the outside pressure goes down by 0.14 times 12, or only 1.7 pascals. The inside internal pressure goes down by 2.4, and the difference is 0.72 pascals. If you have a house on a still day and a sudden gust of wind comes up during your blower door test, on the windward side of the house, that's going to change the house pressure by 8.5 pascals. On the leeward side, it's only 0.7 pascals. That's the key for why we want to measure pressures when we can on the leeward side of the house. So now we're going to talk about some measurements that we and other people have made. So this is some testing that Steve Rogers, the new president of the Energy Conservatory, did just a week ago, a couple weeks ago. And he did this on his house because the wind was forecast to be between 10 and 20 mile an hour, 10 and 20 mile an hour wind for a whole day. So he set up two DG1000 gauges to measure 4 different house to outside pressures with 1 second averaging periods. And so the goal of this test, and he put those on what was supposed to be, during this windy weather, what was going to be the windward side of the house and the leeward side of the house. And he did that to study, so what would the error in the house pressure be if you were actually doing a blower door test during this time when the wind is blowing. So he collected data over about 8 hours, which was the period when the wind was pretty strong. So here's the result, and in this bar chart, we're going to see, so this is the average error that you would have gotten in the house pressure, the induced house pressure, if you had actually done a blower door test. And you can see here that, so this is on the black bar is the windward side. The green bar is the data that comes from the leeward side. As you see, there's really quite a big difference, the windward side and the leeward side. So the leeward side is always much better. And we think that typically, well, in this house, on the average, the error in the induced house pressure on the windward side is 3 times the error in the induced house pressure when measured on the leeward side. So another thing you see from this is, so the errors due to the wind are much less at higher pressures than they are at lower pressures. That's why we generally test buildings at 50 or 75 pascals of pressure instead of at 10 pascals. It's harder to get accurate readings, especially if there's wind, at lower induced pressures. Also, I said that this was the average error due to the wind on the windward side versus the leeward side, the average error in the house pressure. Some, though, were much higher and some were lower. I mean, if this is the average, you can imagine there were pretty big fluctuations. So there were some errors that were much higher and some that were much lower, and the errors are worse at low pressures than on high pressures. So this might seem like it's a kind of a done deal. We know everything about it. I'll just do this. But there's still a lot of research going on, and there were 3 really good papers just at the last AIVC meeting about a year ago. And the focus now is, well, 2 of these studies were about where to measure, the location that gives you the least variation in the baseline pressure. But the other one, which is where a lot of research is being done now, is wherever we measure it, is there some way, what's the best way to take all of the data and analyze it and estimate what the uncertainties are due to the wind pressure fluctuations that we're measuring. So next, we're going to look at some of the ideas. You know, there are all these ideas of where you measure. So we're going to show some of those. Here are some of the things that we tried years ago. I'm going to talk more about some things that we've tried recently, but I'll go over some of these. Sticking the tube in a hose is, you know, a lot of people have come up with that idea, and lots of people think it works, and it doesn't. We found it doesn't make much difference at all. And the tube in a pop bottle with specially placed holes, you know, equally spaced holes, or one big hole that you put here, and how you seal the tube into the end of the Coke bottle. And you know, lots of people have tried that. The problem, and when you put that right down in that place where the house meets the ground, where we think it's the best, the problem is the place that the tube goes into the end of the bottle is no longer on the ground, and what you're really sensing is the pressure at the holes, and those aren't in the right place. So this doesn't work. Using a tin pie plate with a hose connected right in the middle of the pie plate, the idea, and then you space it a 1/4 inch or so off the ground, and the idea is that it measures the average static pressure all around the pie plate, and that made no difference compared to the end of a hose just laying on the concrete. No difference at all. And in fact, I think we had the hose, there's a hose here that's taped to the wall with the end of the hose right at the crack between the building and the driveway. That was much better than the pie plate right next, as closest to the building as we could get it. And then there's this idea, we have done a lot with this over the years. You take 4 long tubes and you put the ends of those 4 tubes that are the same length, so they'll have the same resistance, and that they'll average the pressures. Each of the 4 tubes ends on the middle of the 4 sides of the building, and then they come together into a pressure averaging box that then you connect to your manometer. And this actually did back in the old days when we were using magnehelic gauges, this did seem to help some, but the problem is it's lots of work. And if any of the tube, you've got 450 or 100-foot tubes and they leak, and if the container that they go into, if you touch it for 3 seconds and you warm up that container, the air in the container expands and the pressure goes up. And the, this, although it did help if you were very, very careful, it was not very reliable. And this picture over on the right here shows this is my backyard, 15 years ago or so, where we did a bunch of testing of how to place the end of the tube. And here's something we really thought was, I think I can zoom into this, right? Yeah, here we go. So this thing here is a patented wind averaging device. It's got some tiny little holes located on this tube here, and then some more up here, and then those are connected together and they average. And these plates make sure that the air is going parallel to these plates, and so that you're measuring the static pressure. And this is all connected by a hollow tube that goes down to the bottom where you can connect a hose. So I've got this green hose going into my house, and I'm measuring the house pressure with reference to this averaging device. This is made by the manufacturer of, probably, at least at the time, it was the most precise, accurate barometer that was $3,000 or something, that would measure a hundredth or a thousandth of a pascal of barometric pressure. So really, really sensitive. And they had done all this research and came up with this idea. And then, so we'll come back to that. One of my tubes goes up into the blue sponge this time. The blue sponge didn't work any better than the yellow sponge. And then we have another tube going into the house that is just ending right there. There's the end of the tube. And then there's the fourth location we're measuring the pressure is this yellow tube here that's just down laying on the grass. I didn't tuck it into the grass, which I'm going to show in another slide, but it's just laying on top of the grass. And guess which one worked the best? By far, the tube that just ends, it lays on the ground. That curve, that graph that we saw from ASHRAE that shows the wind speed as a function of the height above the ground, and the wind goes to 0 at the ground, getting close to the ground is way better than any of these things. And as I recall, I think the end of the tube was hardly any worse than this $300 or $400 patented device that this barometric pressure measuring manufacturer came up with. So there are lots of ideas, and most of them don't work. So here's some measurements I made recently. This is the back of my house. So here's a tube that's just out in the middle of my backyard. And this time I tucked it down in the grass so that it's really in the thatch, way down, protected from any direct wind hitting it. Here's some more outdoor pressure taps. I taped a piece of plywood to a window and cut like 8 holes, drilled 8 holes in there so I could run tubes out my house. And this was 3 weeks ago, and it's still there. I'm still making measurements, and we're still working on this and learning something. So we're going to show a Technolog graph in a little bit, and I'm going to point out some labels, and these are the labels that you'll see on the Technolog graph, so we can identify them. So this one is a tube that was just 10 feet long that I've tucked in. I've taken the standard blower door tube, which is a quarter-inch OD, and it friction fits inside of a piece of quarter-inch ID PEX tube, and then that is taped to the wall, and the end of the PEX tube, do we have a close-up of that? Yeah, there we go. The end of the PEX tube just ends right at the crack where the patio meets the wall. The next one is labeled crack. It's this tube that's just laying in this crack. The reason I'll talk more about the PEX tube later, but the reason that's there is to keep rain out. If it's not raining, maybe you can just lay the tube there and not put the PEX tubing and not have to tape it or anything. So we wanted to test that. And then back to this slide, there's another tube that just kind of ends at this in the corner. So it's where the wall and the patio and this wall, the stone wall, all meet. And I've got another one located, just a few inches down from where this arrow ends, where I just taped the end of a tube to a brick. And actually, I also tried one where I put a T connector on the end. A lot of the Europeans all say, oh, you have to put T's on the end of the tube so that the wind won't hit the end of the tube. And I tried putting T's here, and it actually didn't seem to make any difference than just ending the tube there and not having the T there at all. So for quite a few days, I ran Technolog and set it up so I'm measuring at 8 different pressures, the house pressure with reference to those outside pressure taps. And there I showed we zoomed in at that one already. Oh, and here you can see the corner. So this one's labeled corner. Then on the other side of the house, which sometimes was windward and sometimes leeward, I had 2 other pressure taps. One of them, it was actually a little damp here, and it was going to be hard to tape to the wall. So I thought that, well, this is a good case to demonstrate. What I often do is, usually I'll just find a little stick laying in the ground and stick it in the ground and use a twist tie or a piece of string or something to tape the tube so that the tube is pointing down, and that keeps the rain out. The reason the PEX tube is there, if I didn't have the PEX tube and I just took the quarter-inch OD tube and put down here, that would be fine if it doesn't rain. But if it rains and water hits the tube and it runs down, the hole in the tube, which is an 1/8 inch ID, is small enough so that capillary action sucks water into the tube. If you put this larger diameter tube, that is a 1/4 inch OD, and that's too big to suck water by capillary action up the tube. So this works really well to protect against rain getting in the end of the tube. And it's real easy. You can always find something to stick in the ground. Or if there isn't ground there, you can often just tape it or, figure something out. So next we're going to look at a Technolog graph and see the actual noise at just one little snapshot of time, just to give you a feeling for how much difference do some of these things make. So here we're looking at about 2.5 hours of data from all 8 of those outdoor pressure tap locations, and we're measuring the inside pressure with reference to outside. And on the y-axis over here, we see pressures going from -4 pascals to +2 pascals or so. And each one of these data points is 30 seconds, a 30-second average. And so at the beginning of this 2.5-hour period of time, you don't see much going on. There isn't much wind. And then all of a sudden the wind comes up and peaks and then dies down. This was a little thunderstorm. And we're just going to compare some of the signals from these different locations on the outside of the building. These two in this part of the test are on the windward side. And you can kind of see when I turn those off and on, they vary a lot more than the pressures on the leeward side. But so one thing I'm interested in showing here is I'm going to turn off all but one of these pressures. So now we're just looking at the tube that we labeled PEX. That's the one that's on the side of the building as that my office is on, with the brick patio. And this is the tube that's just pointing right into the crack between the house and the patio. And now I'm going to turn on the yellow one, which is the tube that we labeled crack. That's the one that's labeled, that's laying horizontally and is just kind of down in the crack. Or if there weren't a crack there and it was just a sharp corner, you could just put it right down in the corner. And so I'm going to turn that off and on just to show you. And I hope that you suspect that my conclusion is going to be, boy, they look the same, don't they? So it really doesn't matter if the tube ends pointing straight down or you just lay it in the crack. Makes essentially no difference at all. And I think I'll turn the yellow one on again just because we can maybe see it a little better. And then let's turn it off and on the green one. Well, there's maybe a little more difference, but there isn't much difference there. And now let's see what's going on in the grass. Oh, the grass is it's a little different. Of course, it's 20 feet away from the house, but it's on the same side. But is it better or worse? It's kind of hard to tell, and we'll come back to that. And then here's this is the one that's taped to the patio, and I see it has a T on the end. I forgot that. But that also is pretty similar. And then we'll again look at the other side of the building, the west wall, right at the one that's also has PEX tubing on it that was pointed at the ground, right where the wall meets the ground. But there you can see, whoa, that's obviously different. I did want to mention that, you know, any of you that have DG1000s, or if you have a DG700, one or more of them, Technolog is a free download, and you can do this experiment. If you have ideas for how you think you might be able to get the wind pressure readings to be more steady, try them. Run two or four. If you've got 2 gauges, you can do 4 channels at once. But if you just have 1 gauge, run 2 hoses outside and compare the 2, and you'll see which one is better. And you can actually get a pretty good numerical idea if you click on this little button here that shows a rectangle, a white rectangle. I can then go to a spot on the graph and click and then drag a rectangle. And now if I right click, one of the things I can do is say show stats. And this shows me the average reading over that period of time, as well as the scatter. The standard deviation is a measure of how much that data over that period of time is going up and down. So here we can now get get a numerical, a number on how much better one pressure tap is than the other. So these first three are the PEX, the crack, and the corner. They're almost all the same. The east door trim is a little bit better. The grass is also about the same. So even though you could tell, it wasn't rating exactly the same, but on the average, the scatter is about the same. And then on the windward side, you see twice as much noise, roughly, as on the other side. So I next want to just do a little quick summary of what the Energy Conservatory recommends for best practices to try to minimize errors due to fluctuating wind. And well, first of all, if the wind speed's less than somewhere around 5 miles an hour, it turns out it really doesn't matter too much where you put the outdoor pressure tap. So I would usually just put it on the same side of the house as that the blower door fan is on, and just make sure that the end of that outside tube is far enough away from the fan. We say 5 feet, but a little further isn't bad. And what we want to do is eliminate the chance that the jet of air that's coming out of the fan doesn't hit the end of the tube or affect the pressure in any way around the end of that tube. So if you're exhausting, say, into a porch, or there's some obstruction downstream, you might want to move the fan or the end of the tube even further away, just to make sure that the flow field at the exhaust of the fan isn't affecting the pressures at the end of that tube, because that shows up as an error in the house pressure. And we also recommend that the minimum time averaging period be at least 10 seconds. So now if the wind is a little stronger, 5 to 10 miles an hour, now it gets to be worth putting the outdoor pressure tap on the leeward side of the building. So that might mean the best place for the blower door might be on the windward side, but you need to put the hose over on the leeward side. And you can do that in two ways. You can just run a long tube around to the other side of the house from the blower door, or you could run a tube through the house and go out a door on the other side of the house, or out a window. And you still want to have a time averaging period of at least 10 seconds. And then if the wind speed is larger than 10 miles an hour, you want to do the same thing as far as where you put the tube, but now you want to set the averaging time to longer. And one of those AIVC papers that we showed earlier from last year concluded that when there's much wind at all, you want to always have at least 30 seconds for both the baseline and the target pressure readings. And then in these notes, I already mentioned this, it's important that the exhaust from the blower door doesn't impact the pressure measured by the outdoor pressure tap. Placing the tube at the joint between the wall and the ground as low as possible is a good idea. And then if it's going to rain, make sure the end of the tube is protected from rain, because small tubes will wick water into them even when they're pointed down, and you need to keep water out of the tube. We're getting near the end. Before we get to this end section, though, recently we've seen a video promoting a product to be used with a Minneapolis blower door fan that we recommend very strongly against using this device. And this is the Retrotec Smart Cloth. And we've done some testing. First of all, when we saw this, we thought it was going to be a problem. And we've now done some testing and found that, yeah, there's some problems when you use this with, and this might just be with our fan, but it certainly is a problem when you use it with our fan. And we don't make this. This is not our product. We recommend strongly against it. So what this consists of is, in order to try to dampen the wind, they run some very small, I think it's 16th inch ID plastic tubing. You can see in the middle of this circle is where this little tube ends. That's a 16th inch diameter, and it's supposed to damp the pressure fluctuations by having this highly resistive tubing restrict the pressure fluctuations. I think here we go. Okay, yeah, so this is a picture of a blower door. This I think was the last of the fiberglass Model 3 fans from somewhere around 1992. And for quite a while, we recommended, we had a patch with a hole in it to put the outdoor pressure tube through that patch, and our instructions said just stick that hose out there about 1 inch. And then that tube runs to a magnehelic pressure gauge that has a resistor built right into the gauge to cause the gauge to be damped so that you don't see the fluctuations so much. And that part of it worked okay, but we noticed and I think it was about 1992, I was doing a blower door test, and I noticed, because I think I was using a prototype of our first digital manometer, I noticed in some cases when I turned the blower door on that the fan pressure or the house pressure seemed to be doing weird things. And it turns out that, but when you put a ring on, if you feel the flow around the exit of the fan, you'll find that under some conditions, the air actually comes out kind of in a plate shaped. It comes out almost perpendicular, and none of it goes straight, but it all comes out at an angle. And when it does that, I'm not sure that it actually hits the end of the tube, but it creates a pressure disturbance at the end of where this tube is located, which it turns out is just about the same place the end of the two tubes are on the smart cloth. And so we've tested this and we've seen, yep, it does the same thing that we discovered, and that's why we thought we should mention it and strongly recommend against using this product. I'm going to show you a Technolog file that shows you what can happen with the pressures. So in the Technolog file, what I'm going to do is I'm going to connect the tube that connects to these outdoor pressure taps. I'm going to connect that to one side of a channel on a manometer. And on the other side of that channel, I'm running a tube out to where I tuck the hose into the grass. So that pressure channel is measuring the pressure outside at this location with reference to the pressure outside in the grass. And clearly that should read exactly 0. And we'll see that when you turn the fan on some conditions, it doesn't. And at the same time, I connected some T's up, so I was also measuring the house pressure with reference to the smart cloth, and I was measuring the house pressure with reference to the grass. And we'll see on the Technolog file what happened. And I've done some testing in different wind conditions, but I have not tested this extensively. We haven't done any testing using a Retrotec fan. So what happens, presumably they did testing and found out that it worked, but it does not work with the Minneapolis blower door. So here you can see the data file that I gathered with Technolog while I was using the smart cloth, and on the and these are 1 second average readings. And you can see on the left the vertical axis. This is 10 pascals at the top here, and this is minus 200 pascals. The yellow line is the fan pressure. So that gives us an indication. I started out with the blower door fan running at full speed, and then I slowed it down, and I slowed it down again, and I slowed it down again, and then I shut it off. So I'm going to zoom in on this data, which I can do by hitting Shift, and then click and drag, and that will automatically change the scale so we can see what's going on better. Here the blower door fan is off, and we can see the pressure difference between the smart cloth and the grass is real close to zero, as it should be. And since we're not changing that pressure at all, that when we turn the blower door fan on, that should just stay zero. But you can see it jumped up to about 5 pascals, 4.5 pascals, something like that. And these two pressures, the house pressure measured with reference to the grass and the house pressure measured with reference to the smart cloth, those should be the same. But you see the difference of these two is really just the green line. So we can really tell everything that we're interested in knowing by just looking at the green line. You can get very large errors from using this panel. I also found out that it's really sensitive to the exact position of the fan. If you point the fan down a little bit or up a little bit or to the left a little or to the right a little, the green line goes all over. And I didn't really try to find, well, what's the absolute worst? We just found that this is bad enough, so we just have to tell people, don't use this. This isn't appropriate to use with a Minneapolis blower door fan. We also noticed that yeah, it does seem to provide some damping, but as long as you're reading 10-second averages, it essentially does nothing to do any damping. And what I learned years ago is that you should always use digital averaging with an instrument rather than trying to damp something mechanically. When you damp something mechanically, at any instant of time, the reading that you get is not the average. It's not the true mean. So rather than doing this mechanical damping, we think that it's always best to do the averaging electronically. Set your gauge to read 10-second average. You do not get better wind damping by putting a mechanical wind damper in the system. Another thing we noticed is you saw in that picture the small tubes. Well, I have a little roof over my back door that was built 2 years ago. Before that, when it rained, rain hit this door. And if I were doing a blower door test with this smart panel and it rained, the ends of those tubes are going to be very easy to get clogged with water. And because they're so small, capillary suction will pull water into the ends of those tubes. So kind of in conclusion, it might seem that this improves the convenience of doing a test by a little bit, but at least with a Minneapolis blower door fan, it isn't worth it because it introduces potentially very large errors in your house pressure readings, and it just isn't worth it.
Okay, I'm going to jump in. Thanks, Gary, very much for all of the shared data and recommendations. I'm just going to take us and close it out here with one quick summary slide. So earlier, Gary took us through best practices. And this slide shows you how to implement that with your TEC equipment. And so I've re-put the recommended best practices that Gary showed earlier based on the wind speed. And two things to note here. So in that range where you have more than 10-mile-per-hour wind, we said that it's best to increase your time averaging period from 10 seconds to 30 seconds or more. And so I'm showing you here some screens out of our software, the TEC Auto Test. It's actually an app for your phone. And what you can do is once you've set up a project in Autotest and you've geolocated your position and you've picked your standard that you're testing to, you can set up a specific test. And in that section, you'll see there is this time average period and it defaults to 10. You can click right in and put in whatever time average is necessary for your test based on the day and the location of the blower door uh, that you're testing. So that's a pretty easy way to get much better results if it's a windy day. The last thing that I should mention is that on a very windy day or a very gusty day where the wind is changing quite a bit, you might find that if you're using our products in cruise control where it's trying to find the target pressure, that it might wander as the wind goes through large gusts, trying to hold pressure constant. And if you're facing that kind of an issue, you might find that you get better results by manually controlling the fan speed and then increasing your time average to 60 seconds or more. And that might allow you to get some good results on a very gusty day. So that's it. I think now we'll make some time to take any questions that you have. Thanks for joining.
So there was a question at first that said, will the blower placement, windward versus leeward, have an impact on flow readings? And you know, everything we tried to show you, often you can't decide where you're going to place your blower door. You know, it's usually going to be a door that's convenient. If you do have a choice, if you can pick, you want to be on the leeward side just to minimize wind at the blower door as well. But if you follow our best practices, it should have you should be able to limit the impact. Okay, and then I think the second one, it looks like maybe you've typed in an answer, is the reason for keeping the tube out of the rain to prevent wicking into the tube because the droplet can affect pressure. That's exactly correct. That's the issue. And you will see very large fluctuations in those pressure readings if water does get into a small tube. And then maybe Colin, you can answer this last question from Kevin.
Yeah, the question is does it help to test using a door that's inside a porch on a windy day rather than a door directly outside? I think the answer is that it depends on a couple of things. First of all, you have to be a little bit careful if that porch actually affects the air tightness. If it's a fairly tight porch and you have it closed up, you're going to get a large back pressure. And that could be a problem. It could affect the accuracy of the test. It also depends on the wind direction. If your objective was to avoid the effect of the wind, and if you opened up a door between that porch and outside so that it was representative, so that you didn't have the problem I just mentioned before, it would, if it were a cross breeze, you might have made the situation better by using that door directly between the house and the outside. But a head-on wind hitting a door is always going to be problematic, whether you're in a sheltered area or not.
Yeah. Yeah. So I'm seeing we've got a few more coming in. Is there a cutoff for testing if wind speed is above a certain amount? The best practice left off greater than 10. What if the testing is occurring in a coastal location with 20+ mile/hour winds on normal days? I think the answer is yes. Yes, you can test on that. It's a question of, will you meet uncertainty requirements? But if you meet the uncertainty requirements by following best practices, then it's a valid test. Okay, the next one is it okay to set up blower door in the doorway between the garage and the house, outer garage door open? Colin, I think you may have referred to that already a little bit with your earlier answer, but do you want to clarify that one?
Yeah, I think that's going to depend on the program that you're testing under. In other words, the authority that's making the rules for you. The house will give you a different CFM 50 in that condition. The leaks that are between the house and the garage might be a little bit exaggerated when you have that outer garage door open. some people would argue that that's what you want, is you want to exaggerate those leaks because they're leading to indoor air quality issues potentially. But you still have to follow the rules of the program that you're testing for.
This is Gary. Yeah, well, the ResNet 380 standard specifically allows you to put the blower door between the house and the garage. I don't think any other standards prohibit it that I can think of. And I actually think that the standard should require that you open the exterior door or window so that you're actually testing the wall between the house and the garage as part of the envelope, because for indoor air quality purposes, we really want that. That's maybe the most important part of the house, to have airtight so that it prevents pollutants from the garage getting into the house. But if you do that, be careful where you put your outdoor pressure hose. I think the safest thing to do is to take it outside. But if it's a big garage and you can put it, 6 feet to the side of the blower door, the exhaust from the fan, if you have especially the overhead garage door open, the exhaust from the blower door is not going to be enough to change the pressure in the garage. So you still should get a good house to outside pressure if your outdoor reference tube is in the garage, but for sure out of the air coming out of the fan. You just want to make sure that the exhaust from the fan isn't disturbing the pressure where that hose is.
Yeah, related to that comment, Gary, there's a question from Mark. It says, what if the tube is embedded in snow off to the side of a stoop or a walkway? The shoveled area is usually in the blower door airstream, and I think it would be okay, but you probably need to watch out for any water getting into the tube. Is that right?
Yeah, as long as it's out to the side far enough so that it's out of the airstream. I can't say that I tested this with enough detail, but I know years ago when out testing houses on windy winter days, I sometimes threw a handful of snow on top of the outdoor, the end of the outdoor pressure hose, and it seems to, it certainly prevents direct wind currents from hitting the end of the hose, and that, if anything, it's going to help a little bit. Certainly not going to hurt anything. Now, if the hose is really warm, so you throw it out there and it happens to melt the snow and then it wicks water into the hose, that could be a problem, but I never had that problem.
Yeah, it's interesting.
You probably don't want to throw snow on it if it's above freezing.
Yeah, right.
So it's an interesting comment though, and maybe this winter we can look into it a little more, Mark. It's a good question. The last question, Gary, is from Jeff. He says, can you speak to the effects of the length of tubing, resistance and friction, and possible heat gain effect of sun on tube? You referred to it a little bit with that old approach with all the long tubes and averaging the four sides. Maybe you can speak to it a little more.
Well, if you happen to put a restrictor on the end of the tube, the far end of the tube, that can certainly cause problems. But if you restrict the length, and Collins should say more. Collins actually done studies, measured this, but as long as the tube is less than about 100 feet long, when the sun shines on the tube, it does warm the air in the tube, and if the air in the tube warms up, it expands and it's trying to get out of the tube. So it has to go out through the end of the tube that's open, that's outside. If the tube has too much resistance, the air can't freely get out, and so you end up with a pressure buildup in the tube. But I believe what we found is, as long as the tube isn't more than 100 feet long and it doesn't have any little restrictors on the end of it, that it should be okay.
Okay.
Colin?
Yeah, I mean, I think you pretty much covered it there, Gary. The worst case scenario would be that you have a tube that's a larger diameter that's connected to the gauge, so like our standard tubing. And then when you get to the end of that tube, if you have a restriction there,
Yep.
then if there's sun or if there's airflow from the blower door that's blowing on that tube, that's there's going to be more pressure buildup than normal because of that restriction out at the end. If you don't have any restrictions, then our standard advice of using 100 feet or less of 1/8 inch ID tubing is a pretty good recommendation to keep you within the specs for the test.
So I think there's one other thing, Colin, correct me if this isn't right, but the other thing is if you have the outdoor tube and it goes vertically a lot, so let's say you're testing garden style apartments, if you throw a tube off the balcony and then it's a really sunny day and that tube gets warmed by the sun to warmer than the outdoor temperature, that would create a false stack effect inside the tube and could induce errors, couldn't it?
Yes. In that case, you'd want to run that tube in the shade, or if you could possibly find a sheltered location that's at the same level as the blower door, that
Yeah.
would be preferable.
So keep it horizontal. Yeah.
Yep.
You know, this is unrelated. We've got one question that just came in. Susan asked some other questions earlier, and the question is it common practice to run blower door tests from outside the house given COVID-19? And Susan, I've just pulled up our website. I think you guys can see my screen okay. We actually have a document here. If you go to our homepage, there's a link to it right on the homepage, and you'll find that sort of some thoughts on this from us, but also a link to even more recommendations from the Building Performance Association on this topic, and so that will give you some good guidance from BPA as well as some thoughts from us. Looks like Jeff just asked another question. So connecting tubes with nipple connections is a restriction and not a good idea. To reach a leeward side, best practice, one continuous tube, 100 feet. Gary, Colin?
Oh, I think the connectors really don't add much restriction at all.
Yeah,
Okay.
if it's our standard inline couplers, those have nearly the same ID as the tubing itself, and they're so short. So since they're so
Yep.
similar to the tube and they're so
Yep.
short, they have very little effect.
Excellent. Well, again, everybody that hung on, thank you for doing that. This will be posted shortly, and if you signed up with your BPI number, you should see credit within about a week.